Good afternoon. So, what we were looking at last class is basically the various equivalent positions that can be taken up by a general point when you perform a certain symmetry operation on it, and we took the example of the space group P4, right. So, let me take you back to the slide which has the list of all space groups here, all the 17 plane groups, not the space group, the plane groups in 2D, and we were looking at essentially this one. Okay. And when we said that we looked at a certain general point, we essentially meant a point somewhere here, an arbitrary point that was present somewhere there, right, and we performed the P4 operations, the P4 operation, right, or the fourfold rotation operation on that particular point, and we got how many points? We got 4 different points. They were all equivalent by that symmetry operation, that is the fourfold rotation. Okay. And I mentioned that such points are called as general points, whereas there are points, if there is a point which lies on the symmetry element, then you would reduce the total number of multiplicity, you will reduce the multiplicity that is actually possible. So, if you take a look at this P4, so this is the P4 plane group, right. If you have a point right here, right there, right, then the question is, it lies on a symmetry element, right. As soon as you have P4, it essentially automatically generates additional twofold rotation axis at this point, this point, this point, and this point. The presence of the fourfold symmetry automatically entails these additional symmetry. Now, if you have a atom that is lying right here, okay, what is the fractional coordinate of that point? What is the fractional coordinate of that point? So, if you have this to be B and this to be A, you had the twofold rotation right here, right here, right here, right here, and there is a fourfold right. So, the fractional coordinate of this point is half 0. The question is, how many new points are going to be generated when we perform the fourfold rotation? Okay. So, we shall start doing one by one. So, the we have half comma 0 given to us, and the corresponding rotation matrix or the transformation matrix, as you might call it, for the fourfold rotation is this, right. We saw this in the last class as well. So, I am going to multiply it by half and 0, and what do I get? You get half and half, right. I think the rotation matrix is wrong, because a fourfold rotation cannot be producing half and half. What is the rotation matrix for this case? 0, minus 1, 1, 0. So, half 0 will generate what? First 0, it generated a 0 half, right. Now, you perform a fourfold rotation on 0 half. Same thing? Oh, sorry, 0 half. Minus half and 0. Now, you do one more time. So a good question is to see whether these points are actually different or not. So you got, this is 1, so you started off with half comma 0, and you got a 0 comma half, then you got minus half comma 0, and then you got another one which is 0 comma minus half. So with respect to this unit cell right here, this the one that we just started off, this one, okay, where are the other points located? So half comma 0 was located here, 0 comma half is probably located is right here, right? X is equal to 0 and y equal to half. Then x is minus half and y is 0 is located right here, correct? And x is equal to 0 and y is equal to minus half is located here, correct? So if you perform, like I told you, if you have minus half, you can automatically bring it back into the cell by performing the operation 1 minus half, which will give you half. Consequently, this point and this point are basically the same points, right? Similarly, this point and this point are basically the same points, right? So these 2 points which are being generated by the fourfold rotation are already there with you. You are just regenerating them. Therefore, because this particular point, and this is happening simply because this point is lying on the symmetry element that is present there. So such points are called as special points. Points where you have maximum multiplicity, such as a general point here, which has a multiplicity of 4, are called as general points. So when you have a point at half, 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 if you keep applying 1 0 minus 1 1 0 transformation to it over and over again, you are going to generate the same point. Similarly, if you have a point at 0 0 0, you will keep generating the same point over and over again. You will not generate any new points. Therefore, the multiplicity of these points is less. So this was done for the space group P4. So now there are 17 space groups, each one having a different Hermann-Morgen symbols and a different set of symmetry operations that are basically possible, right? And it is possible for us to take a general point in each case. For example, if you take this particular space group, then or a plane group, it is possible for us to choose a general point somewhere here and apply P4MM. You have to apply the fourfold rotation and the 2 mirrors that is associated with it. Okay, and for each and every such operation, you have matrix operations that you can do, which is not required for this class. However, you need to know that there are mathematical operations which can give you the other points that are being generated because of the symmetry. And there are also special points, such as these points marked by the diamond, which indicate a twofold rotation, right? And also mirrors. A point could lie on a mirror, and if it lies on a mirror, it will start generating fewer points than what it did when the point is lying at a general position, right? So for every such plane group, there are specific points called general points where you have a maximum multiplicity, and then you have several special points. Depending upon the symmetry element on which the point is lying, you will generate a certain number of other points by applying that particular symmetry operator. And it is important for us to know what these other points are, right? Only then we can actually have all the atoms that we know in order to recreate the entire 2-dimensional crystal in this case. So it so happens that it is not required for us to actually generate these points by hand. They have already been generated and given to us in the form of crystallographic tables for each and every plane group. Okay, so this is what we are going to look at a little bit today. So we covered all this stuff. So another important point is that in general it is point for more than one atom to actually be located at any general point. So for example, in P4 you could have one general point at point 2, point 3, and another general point could be located at point 1, point 2, and you have to apply all these all the symmetry operators appropriate for that particular plane group to that point to generate all the other points inside the unit cell. Okay, but that is sometimes a cumbersome process depending upon the space group or the plane group that you are dealing with, and consequently people have already done this because it is just based on these matrix type operations. People have already done this and tabulated it in a nice form which you can actually look at. So the website that you can refer to is given right here. Okay, so I'm going to click on it and show you a little bit of that. So this is a very useful website. Okay, you can get a lot of information from this website. So there's something about space group. Space group deals with three-dimensional arrangement of atoms and lattice points. So we're not going to look into that. For the purposes of this course, we would like to look at space group later on. And then now we are dealing with plane group, so we shall talk a little bit about plane group. So we are interested in this link which says plane group symmetry. Okay, the various positions that are essentially there, okay, in which the atoms can be located are called as Wyckoff position. Okay, WY, this one, Wyckoff positions. If you want to look at any one particular plane group, understand what are the various Wyckoff positions possible for that particular plane group, then you go to the website in the same manner that I just did, okay, and then you can click choose it to choose the Wyckoff position that you want, choose the plane group for which you want to look at the Wyckoff position, and the one that we were looking at is this P4, right? We looked at P4, so I am clicking on it and you get a nice table, okay, and they tell you several things here, right? They tell you that this is the plane group P4, right? Plane group P4, right? And they tell you in the first column something called as mult, which is basically the multiplicity of a general point. There is a letter that is associated with each and every position. It starts from A, from the lowermost row. Then there is something called site symmetry. That means a symmetry, if there is a symmetry element passing through that point, then the symmetry of that site. So general point has no symmetry passing through it, which is why you create maximum multiplicity. Consequently, its site symmetry is 1. And if you are given x comma y, the other points that are going to be generated are minus x minus y x, y minus x, and I told you how we can actually generate that in a simple manner. Now if you look at 2C, the position C, 2 dot dot, that means there is a two-fold symmetry axis that is passing through that point. So there are only two different points that were passing through, two different points that you could generate by applying all the symmetry elements associated with the plane group P4, and you got half 0 0 half, and then there are two others, one is half half and 0 0, which is Wyckoff position given by 1B and 1A. Okay. In general, whenever they are going to whenever you want to create a crystal, or whenever you are looking at a literature or a paper and they want to specify a crystal, what they will do is, so whenever you want to create a crystal, what will be given to you is that you will be told that the crystal belongs to a specific plane group or space group, and you will be said that there is an atom at Wyckoff position, say 1A, another atom at Wyckoff position 4D, and there will be the corresponding fractional coordinates associated with it, and a third atom again at Wyckoff position 4D, but now with a different set of fractional coordinates. Okay. In addition to that, since it's a crystal, you need the corresponding lattice constant to actually create this entire crystal. So once you know the lattice constant, okay, the Wyckoff positions of the atoms constituting that crystal, it is possible for you to generate that crystal, because what you will do, you will go to this website. You will go to this website and you will see that there is one atom at 1A. So there is an atom at 0, 0, right? So you will know that there is an atom right here. Then you will also know that there is an atom at 4D. There is one atom at 4D with a specific x and the y value, and another atom with a different x comma y value, right? But you know that for each x comma y value, you are able to generate 4 additional points within the unit cell. So for this atom you will generate 4 additional points, and for this atom also you will generate 4 additional points. So you know all the atoms that are going to lie inside the unit cell. So whenever you see minus x, all you have to do is do 1 minus x and replace it with 1 minus x. If you see minus y, you have to replace it with 1 minus y. Then you know all the points that's lying inside the unit cell, and once you know all the atoms lying inside the unit cell, you can actually generate the entire crystal. So we will see an example of this right now. So this is the P4 plane group, and I have just regenerated that the table right here. Okay, you can also look at it at the website. I just taught you how to do it, and we are going to do a simple problem, and we are going to construct this lattice using MATLAB. Suppose we are given the following: P4 lattice constant is A is given, one atom at Vikov position 0.2, 0.3, another Vikov position C, and another one at A. So these are the various positions that are there for these atoms. So how would we go about writing a simple MATLAB program to generate this lattice and what it means? It's very simple. It's something. Yes.
So the terminology A, B, C, D, it is universal for all the websites out there.
You mean this A, B, C, D? Yeah, it will start from A and keep going up. It will start from A at the lowest row and keep going up in general. I don't think there is a deviation from that. No. That it's standardized. That is precisely the reason. So that I don't have to tell you that it is x, y, minus y. I will just tell you that there is an atom at 4D. For P4 plane group, I will tell you there is an atom at 4D. You just look up the tables to know what 4D means, what atoms are actually present at position 4D. As simple as that. Okay. So what happens is, the code that we already looked at is going to be applicable in a straightforward manner. Okay. For the FCC crystal structure, we defined what is referred to as the basis, right? We got 4 basis atoms using non-primitive lattice vectors to generate the face-centered cubic crystal. In this case, everything remains the same. So I am just going to generate one unit cell. So I have marked N10, N20, N30, and you have these vectors 1, 0, 0, 1, 0, and 0, 0, 0. Because I am creating a plane group, I don't have to have this lattice vector. There is no C lattice vector. And then I have a function here which says basis equal to get basis. We will see what that particular function does in just a bit. Okay. And then the next line is calculating the size of the basis, how many basis atoms are there, and then everything is essentially exactly the same as what we did for the FCC crystal structure. The only thing different is that this line, this is the only line which is different. Okay, so let us see what that line does. This is all that function is. This is another function which is written called function get basis. Okay, what am I doing here? I am defining arrays with the fractional coordinates of those points given to me. So the first point had fractional coordinates 0.2, 0.3, but I know that it generates 1 minus 0.2, 1 minus 0.3, which is basically x bar, y bar from the table, right? So if you simultaneously, if you are able to look at that, it will be nice. So 4D, so the basis D atom has 1, 2, 3, 4 positions present within that unit cell. 0.2, 0.3, which is x comma y, minus x, minus y 0, which is 1 minus 0.2, 1 minus 0.3, 0. The next one is minus y x, which is 1 minus 0.3, 0.2, 0. and the fourth one is y 1 minus 0.2 and 0. Okay. The second one is in position C, that is having just half 0 and 0 half, which is just written down just like that, which is half 0 0 and 0 half 0, and BA is just 0 0 0. Then I concatenate all these positions BD, BC and BA, which is going to be supplied to the main MATLAB program, and that will essentially have the will receive it in the variable basis. So it's a set of all bases for all these points, which I am generating another function and giving it over here, and then when I run this code, it will automatically generate the crystal structure. Since I have given n1, n2, n3 is equal to 0, it will produce one unit cell. So let us see if that works. So this was the point that was actually given to us, 0 comma 0 was given to us, right? One point at position 4a, I think. Yeah, 1 point, 0 comma 0 I gave you, right? Yeah, 1 point at Bilbao position C, another point at Bilbao position A. Bilbao position A means what? There is only 1 point, 0 comma 0, that's it. And then I had these atoms present at the general position. One atom that was present at general position with coordinate 0.2, 0.3. So this is 0.2, 0.3. But on applying this fourfold rotation, I generated this point, and this point. And then I had one more which is present at half comma 0, right? One at Bilbao position B is what I said. So that is this point and then this point. Because this is one single unit cell, I am just generating exactly the number of points that is contained within that unit cell. I don't generate the points that is located at the other end or at x equal to 1, for example. I don't generate a point at y equal to 1, although there must be one. When it will occur only when I translate it. Within this unit cell, there are only 1, 2, 3, 4, 5, 6, 7 points. You can find out the total number of points that is going to be present within the unit cell by simply looking at your table. So that should be quite apparent now. So there is one atom at 0.2, 0.3, another at C, another at A. So you go count here. So if it has at point D, then it has a multiplicity of 4. Therefore, there are 4 atoms within the unit cell, and then one at C. So there are 2 more. 4 plus 2, 6. Then there is one at A, 0 comma 0, 7. So you will get 7 atoms present per unit cell for this particular 2-dimensional crystal. Okay. Now this is a very important aspect. If I now changed my MATLAB program to have a couple of different unit cells, say -1, 0 to 1, and this doesn't matter. Okay, there's some error here. So that's the entire crystal for a couple of different lattices. So how many lattices are there? -1 to 1 means there are 2 lattices. There are 2 unit cells in the x, 2 unit cells in the y direction, right? Or 3, -1, 0 and 1. So -1, 0 and 1. So you can see the three things here. So this no, I don't want it to do that. So this one, this is the second one, and this is the third one. So the third one is not completing because it's the same atom as this, right? If I shouldn't be putting one atom there, if I put one atom there and repeat this entire thing, 2 atoms will basically overlap, right? So this is all the crystal that is going to be generated when you perform the operation in the manner that I just pointed out. So this exercise holds for anything, right? If I am asking you to create even a crystal as your 3-dimensional crystal also, the same set of steps will be followed, and you can actually create 3-dimensional crystals and know the positions of all the atoms in your unit cell. it becomes very important. If you are dealing with very simple things like FCC, BCC, and it's not very, it's very trivial. However, if you are dealing with complicated unit cells, where each unit cell may contain close to 44 or 50 different atoms, then it's just impossible for you to do it without understanding how to do it in the manner that I just demonstrated. Now we will just do one quick exercise. Same thing, P4, the lattice constant A is given, 2 atoms at Wyckoff position D now. There are 2 atoms at Wyckoff position D, okay, one with 0.2, 0.3 and another with 0.1 and 0.3, x comma y, an atom at Wyckoff position C and another atom at Wyckoff position A. So now if you do the same thing, now you have to, BD1 and BD2 are the 2 basis atoms at Wyckoff positions D, and the corresponding values have been written down here based on the table that we just studied. This is the C, this is the atom at A, and I am just concatenating all these atoms and I will generate the crystal. So I think I just have to do basis 2, which is basically the, I just have to change the name of the function which returns me the set of the basis atoms, and I get a crystal structure, a 2D crystal structure, and it's a little bit messy. It might not be possible for you to even see that there is actually a 4-fold symmetry in this crystal structure. It can be pretty hard, right? So let's just take one unit cell and look at it once again. So this is the crystal structure, right? Convinced? So you have one at 0, 0, you have these two ones which are at half 0, 0, half, which is the position C, and then you should have 4 into 2, 8 atoms being generated from the general position. So you do have that 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10, 2 atoms being generated from the position in C and 1 from the one that's being generated at 0, 0. So this unit cell itself has how many atoms? 11 atoms. So you can just now imagine what would happen if you place a complicated molecule with maybe say 20 different atoms at a particular position and apply this space group. It will just the number of atoms per unit cell will be huge. And so now let's look at slightly different unit cells. Other unit cells are pretty straightforward. You have the rectangular unit cell. So all that you're going to do is change the value of A and the B. They're not going to be equal anymore, right? And then you're going to have the third kind of unit cell that you will have is a hexagonal unit cell. But I want to talk about the particular hexagonal unit cell which has the 3-fold symmetry only associated with it. So the given problem is the crystal, the 2-dimensional crystal is in the space group P3M1 with A equal to 1. Okay, one atom is at position A, one atom at position B, one atom at position C. This is all that is given to us. So how would we go about generating the crystal structure? So first, as usual, corresponding website right here, P3M1, okay, and it tells you, again it starts from A to E, it tells you that the general point x comma y generates 6 additional atoms within the unit cell. An atom at B generates 1 and another atom at C generates 1. 2 by 3, 1 by 3, 1 by 3, 2 by 3. Okay. So the multiplicity is given here, 6 different atoms that would be generated by performing all operations corresponding to this plane group on this general atom is given here. Then you have points with multiplicity 1, 1 by 3, 2 by 3 and 2 by 3, 1 by 3 right here. So how would we go about generating the crystal structure, 2-dimensional crystal structure? Firstly, it is important for us to choose a unit cell. In the case of a square mesh, it was very obvious what we needed to choose as a unit cell. Unit cell means what? The corresponding lattice vectors, the lattice vectors per se. So in hexagonal case, as soon as you see P3 or P6, it should strike to you that it has got to be a hexagonal lattice. Okay, that applies even for space lattices. So what we can do is we can choose this to be our one of the lattice vectors. The other one is chosen to be this. This is equal to minus a naught by 2, and this one is root 3 by 2 into a naught, such that the included angle between these two vectors is 120 degree. Okay. It doesn't work if you choose this as B. Only this has to be chosen as B. That works for both hexagonal lattices with 3-fold rotation symmetry and lattices with 6-fold rotation symmetry. Okay. So we will choose A as this, B as this, and construct our lattice. Okay. So let's take a look at our MATLAB code for doing this. So this is my MATLAB code for doing that. So I am going to generate 2 or minus 2, 2 plus 1, 3 plus 2, 5 unit cells in the x, 5 unit cells in the y direction, and so I am going to change these lattice vectors to be what I just wrote down on the slide. So I am going to say this is 1, 0, 0, and the other one was minus 0.5, square root of 3 by 2, 0. What is that? Oh, sorry. Thank you. Right. This is what it generates. So let me just generate it again. Okay. The lines that have been drawn are all the ones which have 120 degree included angle between them. Okay. The dashed lines, the dotted lines, and the thick red lines, the thick whatever the other color lines, and the dotted dashed lines, they are all having an included angle of 120 degree between them. So the environment along those lines should all be the same, because this 2-dimensional crystal has the 3-fold symmetry in it, right? So let us take a look at this line. What color is that, by the way? Cyan. Okay. So you have 2 atoms here, 2 atoms here, 2 atoms here. Looks exactly the same. Similarly, you take the red one. You have 2 atoms, 2 big atoms here, 2 big atoms here, and 2 big atoms here. Now you look at the dashed lines. So you have one medium-sized atom, small atom, and the big atom, right? Medium-sized atom, small atom, and the big atom. Medium-sized atom, small atom, and the big atom. So it's perfectly having this 3-fold rotation in this picture, like what it should have. If you had not chosen the lattice vectors correctly, and for some reason incorrectly chosen the one that I just wrote down, which is basically 100, 0.5 square root of 3 by 2, 0, which is the one with 60 degree included angle, okay, which is a mistake that you can make, thinking that it just needs to be 60 degrees. Now still it must, if it has the 3-fold rotation, it must look like it has the 3-fold rotation, right? Does it have the 3-fold rotation? No. You see, it doesn't have. So choosing this unit cell is extremely important, right? The red ones which have 120 degree between each other, this one has a line of medium atom, small atom, and the big atom, and repeating itself, whereas these two are different from this. So if you rotate it by 120 degrees, they don't really coincide. They don't have the 3-fold rotation, right? So you have to choose unit cells carefully. We can choose any set of lattice, any set of vectors which have included angle 120 degrees between them. Another choice would be say 0.5 square root of 3 by 2, 0.5 minus square root of 3 by 2, which is what? Which is this, right? What am I choosing here? So let me draw it neatly. Okay, this is what I am choosing. Now are the things once again having the threefold symmetry? Yes, right? So this is an important aspect to remember when you are constructing hexagonal lattices. Okay, what is the symmetry that you are dealing with, whether it has threefold symmetry or sixfold symmetry. Okay. So the next I have given you a quick assignment here, which should be very easy to do. All you have to do is click on this link right here, and it will take you to the table which has the P4mm, all the Wyckoff position associated with the P4mm, and you are expected to use this MATLAB script to actually generate the two-dimensional crystal. Okay, should be very simple.